Hello again, I'm Warren Jackson, the father of the hot air scrubber. You may be wondering, can the hot air scrubber really enhance all aspects of indoor air quality? For example, can it take care of PM 2.5 particles or VOCs, other things that may be in the air that didn't come out the lung? You know, things out the lungs, viruses, bacteria, they can come out, they're hot because the body's hot, they rise to the ceiling. But what about those other things, those air pollution particles like PM 2.5. Can a hot air scrubber handle that? And also you may be wondering, how does the hot air scrubber rack up against ASHRAE standard 241, the standard for controlling infectious aerosols? We're going to look at the second question first, and by the time we're through with that, you'll have a good understanding of the hot air scrubber and how it works and what its capabilities are. Here are the CDC recommendations from 2022. They learned that COVID was airborne and people were catching it indoors. So they said you can use HEPA filters, you can put HEPA filters indoors, portable UVC towers. These devices are incorporated into standard 241. Let's look at how well they would work inside an environment that has turbulence. Let's take a look at that. So let's define an overall single pass system efficiency. If we have a source here, air with pathogen in it, some of it's going to escape the device. Here's the device, right? The device is represented by these two blocks. It's got a % capture rate, it's got a % kill rate. When people quote you, this device kills 99.99% of whatever, they're talking simply about this step. Once it gets in the device, how much does it treat? How much does it kill? But you can only kill what you can capture. So you have to look at the system overall efficiency if you're going to effectively evaluate HEPA filters, UVC towers, other portable devices. So if 25% is actually being captured by the device, 75% is escaping. So your overall efficiency for the system is 25%, even though you've got 100% kill, right? You only have 25% capture. You kill everything you capture, so your overall efficiency reduces to 25%. Well, let's do an experiment. Here I have two air defenders. They have a maximum output of 500 cubic feet per minute each. We're going to light a smoke bomb. We're going to turn on the leaf blower at low speed, blow this smoke toward the HEPA filters, and we're going to take a look and see just how much those HEPA filters are actually catching. We're not going to be able to give you an exact number, but we can get an idea and put an approximate number on it. Right now it doesn't look like it's catching any of it. It's actually blowing smoke past the filters. And at the end of the smoke bomb, the whole space is full of smoke. So what would you give that? What would you give that system? Would you say that's 100%? No. Is it 50? Nah. I would say 25%, and that's generous. That is very generous. 25% capture, right? So that takes us back to, see, I had that 25% there waiting on you, didn't I? So the overall capture efficiency, single pass efficiency for HEPA filter in a space with turbulence, it's about 25%. That's not exact, but we know it's not 50, we know it's not 100. It's probably around 5 or 10%, but let's call it 25%. So now let's compare that to the hot air scrubber. The hot air scrubber has these low velocity diffusers. It brings in the air, there's no turbulence. Each diffuser has about 30,000 perforations in it. So let's look at the performance of the diffusers. Here's the diffuser on the left side of the picture there. It's got mom's frying pan with a smoke bomb in it. And you can see that the smoke is rising up. It's not being blown all around like it was with the picture with turbulence in it. Pretty localized. Now that stream will be easy to catch. You can catch that. You can't kill what you can't catch. But we can catch that. Let's take a look at catching it. The plume is rising up to the ceiling, starting to be pulled over to the collection header. Picture 2 and picture 3, you see the collection header working. The manifold is pulling in the smoke. There's no smoke in the bottom. Looks like the hot air scrubber has a capture efficiency of 100%. It's 100%. So the overall system, single pass overall system efficiency for the hot air scrubber is 100%. Looking at the next recommendation, let's put in MERV 13 filters where possible. This is fractional efficiency from 0 to 1 of the filter. This is the particle diameter running from 0.01 to 10. Here's the MERV 13 performance curve right here. MERV 13 is that one. Is this one. So this takes SARS-CoV-2. You go hit a 0.1, you come up to you hit the MERV 13 performance curve, you go over here to the left, pluck off the efficiency. You get a number like 49%. Let's call it 50%. The kill part is only 50%. We're not even talking about the capture. The capture is 25%. The kill part is 50%. So overall efficiency is going to be about 12.5%. You multiply those two percentages together, get the overall efficiency. These last two maximize your purge rates. 241 standard came and said, well, how much, instead of just qualitatively saying maximize it, they actually put numbers on what the purge rate should be. So let's just lump these last two together and look at operating a system with no recycle. What does that do for us? Here you've got fresh air being brought in at a much higher rate, 5 to 6 times the normal rate, because we're in infection risk management mode under standard 241. This block diagram here, this represents the enclosed space. Fresh air in equals the exhaust air out. We're putting energy in, it is turbulent, it's well mixed, so as the exhaust air goes out, so does your energy. You remember that. Come on, you guys remember that when your grandpa used to yell at you and say, hey boy, close that door, we can't afford the heat the inside and the outside. That's what we're doing here with no recycle. We're trying to heat the outside. You can't operate like that for too long, you'll be broke. The hot air scrubber we use, HEPA filters, we can use UVC light. So we're not dependent on dilution and high purge rates to control infectious aerosols. Hence, you can recycle a lot of your air back into the system. And of course, as you recycle your air, your heat follows your air. So the hot air scrubber ends up being 80% more efficient from the energy standpoint than going into infection risk management mode as given by standard 241. You also have reduced capital investment because, let's go back a chart, because when you go into risk management mode and you turn this airflow up, it's 5 to 6 times normal airflow. That means you have to have essentially a separate air handling system to carry that much air. If you build a system to carry that much air, you won't be able to run normal operations because the turn down in that system would put your motors operating in a zone where it's not very efficient. So you don't want to design right there, okay? So we still have some holes in the standard. There's some holes there, and let's tighten these things up, okay? We're gonna bring forth a new postulate. Let's say that the best system, we're gonna say, minimizes the time that the air pollutant stays in the occupied zone. Let's take a look at that. And we're gonna get rid of turbulence. We're gonna change the system to upflow, because wonderful things happen when we change the system to a non-turbulent upflow system. Air force is on a stationary particle. You've got the buoyancy force. Buoyancy force is proportional to the difference in density between the particle and the fluid in the surroundings. The gravity of force points downward. That's F equals ma. If the gravity force is the greater force, if it's greater than the buoyancy force, the particle falls to the floor. That's what's happening here below the red line. We've got particles that are falling to the floor. You can come along with a vacuum cleaner and pick up your dust and your pollens and things that fall to the floor. Things above the line, they're light, they want to go to the ceiling. Their density difference is higher than the force of gravity. Right? Air upflow lets you take advantage of that, and it also reduces the time that pollutant particle stays in the occupied zone. But before we get into defining the occupied zone, can the hot air scrubber handle things that are in the air that are not hot, like PM 2.5 particles? Well, yes, it can. Let's look at the dynamics here of this plume. The plume has symmetry to it because there's no turbulence in the room. This plume is narrow at the bottom. As you get higher, the plume gets wider. Why is that? Have you ever thought about that? That's because as the hot air rises, you're pulling in some cool air into the plume from the surroundings. And the higher up you get, the more air that's inside the plume, so the plume gets wider as you go up. It's going to eventually reach a temperature inside the plume that's equal to the outside, the surrounding temperatures, and that plume's going to stop rising. But that's why the plume has the shape that it has in a non-turbulent environment with upflow. The plume is created by the body. So you've got this plume coming off of the body of the human, and here's a PM 2.5 particle floating around in the room. What's going to happen to it? We saw that on the previous chart. It's going to get pulled into the plume, and it'll be swept up. It'll be carried up toward the ceiling. Our collection pipe with 100% collection efficiency is going to grab all of that stuff, and we're going to be able to filter it, or we'll be able to zap it with UVC light, whatever we want to do to it. Okay, it's at our mercy once we capture it, but we have to capture it first before we can do anything to it. That's where the hot air scrubber excels, in the capture system. So now we're ready to move into the occupied zone. With upflow and turbulence out of the picture, the height of the occupied zone is the height of a human here. So let's say we have a human that's 2.14 meters tall, that's 7 foot. And we have a PM 2.5 particle at the bottom of the zone. It's going to ride through the zone and out the zone following the thermal plume. So the velocity of the particle is going to be the velocity of the human thermal plume. So how long does it take the particle to get out of the occupied zone? This is a standard distance time problem. Let's say you are 120 miles away from Bug Tussle, USA. You're going to average 60 miles an hour. How long does it take you to get to Bug Tussle? It takes 2 hours, right? This is the same problem. So you do your arithmetic, and it requires 7 seconds, just 7 seconds, for the particle to get out of the occupied zone. When you go with turbulence, you can calculate the time that particle stays in the zone using the CFSTR model, continuous flow stirred tank reactor model. And that says simply that the time a pollutant is inside this room is equal to the volume of the room divided by the purge rate through the room. For you HVAC engineers out there, the hold-up time is the reciprocal of the air changeover rate. For ash rate standard 241 with a purge rate of 6,000 cubic feet per minute, you have a hold-up time in the zone of 4.5 minutes. This compares to the hot air scrubber, which was only 7 seconds. So there we have it. We asked the question, does the hot air scrubber, is it compliant with ASHRAE standard 241? Well, the answer is yes, in spirit. The CDC recommendations from the 2020 pandemic, that is the basis for ASHRAE standard 241. There's some holes in those recommendations, okay? That comes out of, we have microbiologists, medical doctors, epidemiologists in the CDC. They understand the bugs. They don't understand HVAC systems, the mechanical side of things. We have mechanical engineers, HVAC engineers. They understand their system. They don't understand chemical reactor design. So the hot air scrubber represents synergy between both sides, the medical side and the mechanical side. In designing the system, we defined a single pass overall efficiency number. It's not just enough to look at what a device kills, but you also have to look at what percentage in the system that the device captures. You can't kill what you can't capture. It requires both. We postulated a new theorem that the best HVAC design will minimize the time that pollutants spend in the occupied zone, and we found that the hot air scrubber removes these pollutants 40 times faster than the dilution strategy. We also saw it can handle cold air pollutants like PM 2.5 particles. Now, this is important. There's a general flaw in the current strategy of going from normal operation to infection control. That's what's described in 241 standard. Someone has to tell us to switch from normal operation to infection control. That was the CDC, but CDC is not going to be able to tell us that anymore. It's being dismantled. Not only that, anti-vaxxers are running the show. So we're seeing more measles. We're going to see whooping cough. We're going to see rubella, chickenpox cases. The hot air scrubber can catch all of those and treat all of those childhood diseases as well. So the politics can change. The head of the CDC public health system can change, but with the hot air scrubber, the pipes are constant. They don't change, so our protection will still be out there despite what the government and what the politics are doing. So we're counting on you infrastructure companies. If you solve problems, the marketplace will reward you for it. We've got a infrastructure licensing fee plan to reward you for driving this technology out into the field. So we're depending on you to help make America safe again for our children and our children's children. I thank you again for tuning in and listening.